My topic today is pig on test, low latency data processing with big data. My name is Daniel Dai. I am software engineer in Hortonworks. And I have a co-author, Rohini, but unfortunately, he cannot be here today. But Rohini did a lot for pig on test. He is in the team in the beginning. He contributed a lot to the pig on test code base. And now he is driving the pig on test production inside Yahoo. So she put pig on test on the Yahoo's research cluster, which is huge clusters. The largest one contains 6,000 nodes. So he fixed a lot of things during this process. So thanks, Rohini. This is my agenda. First, I will introduce the team, and then I talk a little bit about Apache Pig, and then I talk about why we need to do the pig on test project, and then we look into pig on test in detail. So we'll go through the design and the test features we use inside Pig, and we talk about performance, and then we talk about the current status for pig on test, and then we talk about the future plan. So here is the team. This team is kind of special compared to other projects. There is no single company driving the development. Instead, we have a virtual team, which consists Rohini and Olga from Yahoo, Chun-Su from Netflix, Mark and Alex from LinkedIn, and me from Hortonworks. So we basically work independently, but in a very coordinated manner. We have weekly stand-up, and we have sprint. And we use Apache to collaborate. And finally, this model turns out to work very well. And actually, Chun-Su and Mark gives a talk in last year's ApacheCon just to talk about this model. And let me spend one slide to talk about what is Pig. Pig is a data processing language. It is SQL-like, but there's some difference. Pig is a procedural language, so it processes data step by step. Here is one example of Pig script. So you first load the data into alias A, and then you do filter, and you only retain the age, certain age group of this relation. And after that, you do a group. And then you do a for each to get the age and the average GPA for that age group. And then you store into HDFS. So unlike SQL, you don't have to scramble everything into one single SQL statement. This is more natural and intuitive. And Pig can process HDFS file directly, which means you don't have to create a table. And you don't even need to schema. And Pig's motto is, Pig eats everything. And Pig is also feature-rich. It has the features which SQL doesn't have, such as multi-query, nested for each, scalar, algebraic and accumulator UDF, and non-Java UDF, and distributed order by and skill join. Pig is also Turing complete, which means you can write macro, and you can also embed Pig into Python script so that you can use the looping and the branching features of Python. We typically see two types of two groups of people who are using Pig. ETL people use Pig because Pig syntax is very close to the ETL tools. The Pig operator, such as filter for each group join are also can be found in ETL tools. Another group of people who like to use pig are the data scientists. So they need a rich feature which pig provides. They want to use the nested operators. They want to write Python UDF. And they want to embed pig inside Python to do the looping. As for the pig users, we see a lot of companies is using pig. At Yahoo, 60% of total Hadoop jobs is run by pig. And altogether, there are 12 million pig jobs monthly. And other heavy users include Twitter, Netflix, LinkedIn, eBay, Salesforce, and etc. Pig traditionally built on top of MapReduce. MapReduce is good. It is stable, and it is scalable. MapReduce provides a simple API, but in the meantime, it is very restrictive. So things works very well at the beginning. However, when more and more workloads migrated to pig, and more people depend on pig to do their daily job, they request something more. They want pig to be fast. However, with the restriction of MapReduce API, pig cannot process data as fast as it can. So we are looking for a new execution engine. And the new execution engine must be general DAG based. That's what a traditional database system execution engine based on. So we can do everything a traditional database system can do. And we need a powerful API to deal with the complex requirement of pig. In the meantime, we don't want to change things completely. We want to continue to use Hadoop cluster. We like the stability and the scalability of Hadoop. We also want to continue to use the enterprise features of Hadoop, such as security, multi-tenancy enabled, encryption, learning upgrades. So after we evaluate different kinds of DAG execution engine, we feel Tez fit our needs the best. Tez is a low-level DAG execution engine. The API is very complex compared to MapReduce, so it is not end-user facing. However, for things like pig hive cascading, it's not a problem because these tools can hide the internal complexity and not expose to the user. Tez offers a rich API, so we can define vertex, edges with semantics, and we can use plugin to customize the DAG behavior. Tez is fast, whether you have a lot of memory or not. So if you have memory, Tez will make use of it. If not, Tez still perform fast than MapReduce. Tez is resource efficient. Compared to MapReduce, it uses much less nodes to process data. And Tez is built on top of Yarn, so it inherits a lot of features of Yarn internally. It is multi-tenancy enabled. It is scalable. It is relatively stable as a new execution engine because it leverages a lot of existing MapReduce code. So you can use Kerberos for security. And last but not least, the test team is awesome. Thanks because Sid, Hitesh, Jeff, and Rajesh. So they provide excellent community support. If you hit issues, you can count on them to solve it quickly. So let's look at pick on tags in detail. So here is the overall design of pick on tags from a high point of view. So first, we will compile a pick script into logical plan. And from the logical plan, we will translate it into physical plan. And then, depends on the execution engine user choose to run the pick script, it will translate into either a test plan or a MapReduce plan. So in this diagram, we can see the test plan is in the same position as the MapReduce plan, which means we don't translate MapReduce plan into test plan to implement pick on test. Actually, you can do that. You can translate MapReduce into test, and actually, Archer from Twitter did that and make it work. But eventually, we think the DAG processing is the future for pig, and we want to get it right in the first place. So we drop that initial work completely and build from scratch. So let's take a look of a typical pig plan, pig script to see what did we do in the test plan. So this is pig script, load the data, and then do group on different keys. And after that, we join the result of two groups. So typically, we require 3 MapReduce jobs to do that in MapReduce. So the first MapReduce job will do the first group by, and the second MapReduce job do the second group by, and the third MapReduce job do the join. But pig has an optimization called the multi-query optimizer, which can combine the first 2 group by together. So we end up with 2 MapReduce jobs. The first MapReduce job will load the data from HDFS, and then do 2 group by simultaneously. And after that, we will dump the intermediate result into HDFS, and then the second MapReduce job will load this intermediate result from HDFS and then do the join. Let's take a look of the test plan in the right. So in the test plan, we load the data from HDFS and send it to different vertexes. Because of in test plan, we only load the input date once. So we don't have to use the multi-query optimizer to combine these 2 vertices. So we can just use the 2 vertices. And then after the 2 group by, we will send the output of the group by to the last vertex to do the join. So compared to the MapReduce plan in the left, we can see there are several benefits of test plan. So first, in the MapReduce plan, we have to dump the intermediate result into HDFS and then load it back. We get rid of this step in the test. And the second, if you take a look of the test plan, it is more straightforward. So every node just do a single job. For the MapReduce plan, because not too many people will understand what is multi-query optimizer and what it's doing. So if things happens, if something wrong, it's very hard to debugging and reasoning for the normal user. So let's take a deeper look of the test DAG to see what exactly happened for a test plan. So this is the pick script we just talked about. So we have 2 group by, and after that we do a join. And vertex 1 load the input data from HDFS just once. And just like MapReduce, it will partition the data and send it to the output vertex. And please note, we have 2 output vertex here. So the vertex 1 will partition the data on the different key independently and send 2 different copies to vertex 2 and vertex 3. And the vertex 2 and the vertex 3 each will do the shuffle and the sorting. And after processing the data, vertex 2 and vertex 3 will partition and shuffle the data on the same key to vertex 4, which will do the join. So we can see the processing of tags is very similar to MapReduce, except we don't have to store the intermediate file into HDFS. All the data movement in this diagram are essential because we need to do the shuffle to perform group and join. So this DAG is very optimal. And let's take a look of the order by. So in the pick order by case, in addition to the benefit we just talked about before, we don't have to use the intermediate file on the HDFS. We actually use a lot of task-specific optimization in the test plan. So we can see in the right side, this is the test plan. And we use different edge semantics. We use the broadcast edge, and we use the one-to-one edge. So we use the broadcast edge to broadcast the sample. So for those who don't know about pig, so for pig to do the order by, we first need to sample the input data and get histogram. And we will broadcast this histogram to the downstream node to do the further processing. So we use the broadcast edge to do the to distribute the sample file. And then we have one-to-one edge. So people may wonder why we have one-to-one edge, why we cannot combine this one-to-one edge together, because the processing actually divided into two parts. The first part don't require this sample file. And then in the middle, we build a sample file and send it to the second vertex. So the second part needs the sample file. So actually, we need to use the one-to-one edge and divide this step into 2. And also, we will cache the sample file in the object cache. So when the container reuse happens, they don't need to build the sample file again and again. They can cache the object into the memory and use it in the next container. So Pig uses a lot of features and customizations of tags. So we need to customize the vertex, and we need to customize the input and output between vertices. And we need to use Vertex Manager to tune the parallelism of vertices. Here, I will give you some example. So the vertex need to be customized. That's obvious. The vertex is the place pick run the data pipeline. So we need to customize the vertex to process the data properly. And we need to customize the edge as well. Unlike MapReduce, which blindly partition, shuffle, and sort data between map and reduce, we can do more flexible customization in TES. In many cases, sorting is not necessary. For example, union only need to combine two inputs together without sorting. An example file in the order by and the right relation in the replicated join only need to be broadcast, but without sorting. Also, in MapReduce, we only do scatter gather between map and reduce. If we want to do a broadcast, such as distributor scalar, we will have to use a very hacky way. The most common hacky is to put the file onto HDFS, and then every task read from HDFS. This is very problematic because thousands of tasks read from HDFS, it will very easily to take the name node down. A better hack is to use the distributed cache. Why this is much more better than the HDFS approach? We still need to hit the HDFS multiple times, since every node manager need to read from HDFS and localize the distributed cache. And in TES, we don't need a hack. We can use a standard broadcast edge to do that. We will read from HDFS only once, and then broadcast the file over the network. So another edge type is the one-to-one edge. In that, one task will and only will process the output of a particular upstream task. So pick use one-to-one edge in order by and also in skewed join. In such case, TES will schedule two tasks on the same node manager, thus completely avoid network traffic. So next feature pick use is the session reuse. So for every MapReduce job, we will need an application master. The job of application master is to launch map task and reduce tasks. So after the MapReduce job finish, we kill the application master. And the next MapReduce job will launch another application master. So a pick script usually contains dozens of MapReduce jobs. So that's a significant delay and a waste of the resource. And since application master is only doing admin work, not the real work we need MapReduce to do, and this often leads to resource congestion. So in one extreme example, we see hundreds of application masters running on a cluster, but no real work can be done because there's no container available to do the real work. So no one can actually make progress. And TES solve this problem completely. For a TES DAG, which usually represents the workload of a dozens of MapReduce jobs, requires only one application master. And further, even if the DAG finishes, TES does not kill the application master. Instead, the same application master can be reused to launch another DAG, which is called session reuse. This benefits pig a lot. Typically, we will compile a pig script into a single DAG so that only one application master is required. And there are a couple of cases which pig need to submit multiple DAGs, such as multiple exec statement in a pig script, and multiple DAG launched by a grunt session, multiple DAG generated by a loop inside a Python script. In that, pig will maintain a session pool and submit the DAG to the existing application master whenever possible. And container use is even more useful. So container is the place where pig run the data pipeline. In MapReduce, once the task finishes, we kill the container JVM. A large MapReduce job may contain several thousand tasks, which means we need to kill and restart JVM thousands of times. And further, in some vertexes, we need to spend time to initialize the resource. For example, in replicate join, we need to load the right side relation and put it into the memory. And we need to do that thousands of times as well. In a congested cluster, requesting a new container means you have to wait in a line and compete the resource with other jobs. And we also need to do that thousands of times. In Tez, we don't kill the container immediately after the task finish. Instead, we try to reuse the container whenever possible. The first task can cache any memory object into a key value store called object cache. The next task will retrieve the object by name from the object cache. Pig use object cache to store the right relation of the right table in replicate join, and the example file in the order by and skew join. With container reuse and object caching, we minimize the cost of killing and restarting JVM, initializing resource, and compute resource in a busy cluster. So we see significant speed up for replicate join, and we see order of magnitude speed up for smaller pig jobs. One thing to note, however, customize pig load func, store func, and UDF might need to be hardened. Since Tez will reuse the same JVM, static variable needs to be reinitialized when the vertex start, and some memory leak, which is not obvious in MapReduce, may cause issue in Tez. Another optimization is Vertex Group. So look at this example script. If we do it in MapReduce, we will need 2 MapReduce jobs to process it. The first MapReduce job will process 2 group by simultaneously, thanks for the multi-query optimization. Otherwise, we will need 3 MapReduce jobs to process this pig script. The second MapReduce job only do a join. Its job is very simple, just combining the 2 outputs together. And in Tez, we introduce a concept called Vertex Group. It is a virtual vertex which moves the output of the 2 group vertex into the same folder. Thus, we avoid a real Tez task. So let's talk about the automatic parallelism. In Pig, user can set parallelism manually in the parallelism statement, or define a global default parallelism in Pig script. However, set parallelism manually is hard. Users usually don't have idea how to set parallelism properly. In MapReduce, we use automatic parallelism if user leave the parallelism blank. And we continue to do that in TES, and we can do it better. So there are multiple layers of parallelism adjustment in PIG. At compile time, we estimate the parallelism of each vertex based on the DAG input and the data pipeline inside every vertex. And this is very rough, however. Unlike Hive, which is able to collect data stats and save it into metastore, PIG don't have the stats of the input data. So when the DAG progress, we will find we either underestimate or overestimate the parallelism originally. Vertex Manager provides an opportunity to monitor the DAG progress and adjust the parallelism dynamically. So we use the dynamic parallelism in PIG. So when a vertex is about to start, Vertex Manager will estimate its input data size and adjust the parallelism of the vertex. This is called dynamic parallelism. The most common Vertex Manager is already implemented in TES, which is called the Shuffle Vertex Manager. It is able to handle typical scatter-gather edge. There are other Vertex Manager available in TES, and of course, you can implement customized Vertex Manager and did that for order by and skew join. So let's take a deeper look into Shuffle Vertex Manager. It is widely used in PIG to perform most operations need shuffle, such as group, hash join. In this scenario, we initially set the parallelism to 4 for the join vertex. When the join vertex is about to start, we find the actual data coming out of A and B is less than we estimated. So we will only need parallelism 2 according to our policy. So Shuffle Vertex Manager will get this notification and decide to change the parallelism. So we eliminate task 3 and 4. Notice vertex A and vertex B is already started, so the output data is already partitioned into 4. And TES, in this scenario, TES will do something very sophisticated. It will reroute and reroute the partition originally goes to task 3 and task 4 to task 1 and task 2. And thus, the parallelism of the join vertex is changed to at runtime. Note the way Shuffle Vertex estimates the input data size of join vertex. It waits for a certain percentage of the input task finish, then estimate the input size based on the finished task. If the input tasks are highly skewed, this is problematic. And also, Shuffle Vertex Manager only decrease the parallelism, but not increase. Decrease the parallelism only need to reroute the eliminated partition to existing tasks. On the other hand, increase the parallelism requires to repartition the existing partitions, which is harder to do. And order by, on the other hand, estimate the parallelism based on the sample collected. In order by, we will first sample the input data to decide how many tasks to be used in sorting, and the key range for every task. This number will send to the vertex manager of the sorting vertex. Since the upstream node is not started yet, which means input data is not partitioned, so we can freely adjust the parallelism of the sorting vertex, either decrease the parallelism or increase the parallelism. The upstream vertex will then partition the data with the right parallelism. And because the data size is estimated based on a complete random sample of the input data, it is more accurate. So when we discuss about shuffle vertex manage, we already covered the limitation of it. We can only decrease the parallelism, but not increase it. And also, there is overhead involved when we reroute the partition. So it is better to get things right before the upstream vertex start. And this is why we need another layer of parallelism. And we call it the peak-grace parallelism. The idea is when the DAG progresses, we adjust the parallelism of the downstream vertex accordingly with the better estimation. Even when shuffle vertex manage cannot bring everything right, it will not off too much. So this diagram shows an example of peak-grace parallelism. So based on the input size of the data, we do a rough estimation of the DAG. So depending on the input size, we have accurate estimation of the upstream vertex A, B, and F. And then if we look into the data pipeline of each vertex, we do the rough estimation of the DAG, such as if we see there's a flatten in the data pipeline, we increase the parallelism. If we do a filter in the data pipeline, we decrease the parallelism. However, this is very rough. And then the shuffle vertex manager will get a notification that A and B is finished. So we can get very exact number of the output data size of A and B. And use this information, we will adjust all the vertices downstream. And then we get notification that the node F is finished, and we get the accurate output data size from it. And then we adjust the downstream vertices again. And we will do the same thing for the vertex C. So when the DAG progress, we can see we will gradually change the parallelism to the best knowledge we know at that moment. And let's take a look at TES UI. So the TES team did a great job, which you will have a nice UI to see your job. So this is functionally equivalent to the MapReduce web UI. And actually, you can see things better. So this is the diagram of a particular pick script. So you can see all the vertices of this pick script. And this should be very close to the logical view of this pick script. And with the test UI, you can see the DAG graph, and you can see the application, the DAG inside the application, and the vertices inside the DAG, and the task attempts. And also you will have the swim line, which visualize the containers Tez is using. And you can see the counters of the job. And the Tez UI is built on the Young timeline server. The Young timeline server is in active development, and we will benefit from the scalability improvement they are doing right now. And it is possible to extend what we have already. So we can have a pick-specific view. So you will see which DAG is launched by the pick script. And also, we can customize the Tez UI. So for every vertex, it will show the pick code snip running inside the vertex. So here, I share some performance data. And this is the performance data from Yahoo. And the first job is a simple MapReduce job. And we can see in MapReduce, it takes 28 minutes to run. And in Tez, it's only 18 minutes. And in the second pick script, it is a little bit larger. It has 12 MapReduce jobs. And we can see in MapReduce, it takes 11 minutes. And in Tez, we only use 5 minutes. And the third job is relatively complex. And we have 4 MapReduce, but it's processing 8.4 terabytes of data. And on Tez, we only run 35 minutes and 50 minutes on MapReduce. So we can see the improvements is quite consistent. And here we look into the data size for MapReduce job and the Tez job produced in a single pick script. So in this pick script, the MapReduce will read almost 7 gigabytes of data from HDFS. And for Tez, it's only less than half of it. And for MapReduce, it will write more than 7 gig of the data into HDFS. And in Tez, it's only 5 gig. And we can see in this particular pick script, we see 2.9 times speed up. And here's the performance number from Netflix. And they also run different pick script and also see consistent performance improvements. And besides the heavy-duty ETL job, we also tested pig on Tez to run the interactive query. So here we take one of the TCP edge query and run against the different input data size. And when the input data size is big, like 10 gigabytes, we see the speed up as we see before in the heavy-duty ETL job, which is 2-3x. And then we decrease the input data size. We decrease into 5 gig, and we see 3.4 times speed up. And we further decrease it into 1 gigabyte. We see 4.8 speed up. When we decrease the input data size to 500 megabytes, we see 6 times speed up. So So as we expected, when the input data size is small, the speed up will be higher. This is because we will use the container reuse. And when the data size is small, the latency saving for tests will become very obvious. Another test we did is the iterative algorithm. So PIC can write the iterative algorithm using the PIC embedding. Okay. So we take an algorithm, k-means algorithm, and run it again and again. So we run it in the 10 iteration, we see 5 times speed up. And if we run it 100 iteration, we see 14 times speed up. The observation we find is the first iteration in test takes a long time, but after the first iteration, it only takes around 1.5 seconds for every iteration. So test container reuse contribute the speed up for this. And because we run out of time, we skip this slide. So we know what the performance coming from. It is from not to write and read from HDFS, and from the container reuse. Okay, let's skip this slide. And we talk about how to deploy pick-on test on your cluster. Actually, it's very easy. Both test and pick are just client-side library. There is no server process. So all you need to do is, for pick, you put for test, so you put the test table onto HDFS, and that's it. And for pick, all you need to do is when you run test, you just use a flag called -x test, means please use the test engine to run this pick script. So the user impact is very low. There's no ops cost, so it's very easy to deploy. And the pick on test is already released. Pick 14 release actually contains it. It's released in last November.
So that's all we have time for. We have to transition to the next one.
Okay, all right.
It's literally starting in 2 minutes, so
Okay.
we've got to cut you off there.
Okay, so do we have time to question?
No, the next track starts in 2 minutes, so
Okay,
the speaker has to come in.
all right.